Welcome to TalkTensors. This is the place where we cut through the noise, ignore the marketing fluff, and get straight to the signal in machine learning and those viral tech trends you're seeing everywhere.
Yep.
If you're trying to keep your head above water in the flood of ArcSIF papers, you're definitely in the right place. I'm your host.
And I'm joining you to help parse the math from the magic. It's great to be here.
Today, we are tackling something that I know has been keeping a lot of our listeners up at night.
Oh, yeah.
If you follow the AI space, you know we are in the middle of a very specific, very intense hype cycle. I'm talking about the obsession with reasoning models.
It's all anyone's talking about. You know the names S1, R1. It's unavoidable.
Exactly. We've seen the screenshots. We've seen the benchmarks. We see these models solving PhD-level physics problems. We see them coding entire applications in one go, fixing their own bugs and writing out these long, thoughtful chains of logic.
And the narrative is always the same. This changes everything.
Right. And look, to be fair, it does represent a pretty big paradigm shift.
It really does. I mean, we've moved past the era of just next token prediction, acting like a fancy autocomplete.
Right.
And we've entered the era of test time scaling.
But here's the hook, and this is really the problem we are digging into today. Everyone sees the results. Everyone sees the amazing test time scaling. But the actual recipe,
the secret sauce,
the specific engineering blueprint for the reinforcement learning, the RL that powers these things, it's been a complete black box.
It has. The big labs might release the model weights or, they release an API so you can rent the intelligence.
Sure.
But they rarely release the training code. And they definitely don't release the specific algorithmic tweaks that make the reinforcement learning stable.
And that's led to a lot of frustration in the open source community.
Frustration is putting it mildly.
I've been reading the forums. You have incredibly smart engineers, really talented people trying to reproduce these results. They take a standard llama or a Quinn model, they try to use the standard algorithms, and they are just hitting a wall.
They're crashing and burning. It's not working.
They end up with this thing called entropy collapse. The model just stops exploring. It turns into a zombie.
When the training loss curves just go haywire. Spikes everywhere.
It's the missing manual problem, right? We know what they're doing broadly, reinforcement learning from human feedback, but we don't know the specifics. We don't know how they are tuning it to get that reasoning behavior to emerge without the whole thing just falling apart.
Well, today, that might be changing. We're unboxing the solution. We're doing a deep dive into a system called DTO.
DIPO, that stands for Decoupled Clip and Dynamic Sampling Policy Optimization.
It is quite the mouthful.
It is, but the thesis for this whole deep dive is simple. This isn't just another paper. This is a fully open source system code data algorithm that breaks open that black box.
And it doesn't just match the state of the art. In some very specific, very hard benchmarks, it actually beats it.
Okay, so that's a big claim. What are we talking about specifically?
Specifically, this system takes a Quinn 2.532B model, which is, a strong but pretty standard mid-size model, and it boosts it to 50% accuracy on the AIME 2024 math benchmark.
Which is huge. And just for context, AIME isn't basic arithmetic. These are American Invitational Mathematics examination problems. They're competition level.
They are very difficult. And for even more context, the previous open weight benchmark from DeepSeek's R10 pipeline on the exact same model was around 47%.
Okay, so DAPO is squeezing out more performance.
It is, but the real kicker is efficiency. The headline number is the score, but the story is how they got there. They reached that 50% score with only half the training steps the DeepSeek run.
Half the steps, so they are learning faster and learning better.
Precisely. And they did it by diagnosing 4 specific diseases of large-scale RL and then prescribing 4 specific engineering cures.
And that is our mission today. We are going to unpack those 4 pillars of DPO. We're going to look at how they fix the broken RL pipeline.
And we're going to discuss that magical moment when the model actually starts to think. When reasoning behavior emerges from all that noise.
Including, I see a fascinating case study about a tetrahedron problem that I think really illustrates what's happening under the hood.
Oh yeah, that one's a good one. It's a real light bulb moment.
Okay, let's get into it. Before we dive into the nuts and bolts of DPO itself, we really need to set the scene. You mentioned test time scaling. I feel like this is a buzzword that gets thrown around a lot, but I want to ground it. What does it actually mean in this context?
Right. So traditionally, for years, we focused on training time scaling. You make the model bigger, you give it more data, you train it for longer. That's how we got from, say, GPT-2 to GPT-4.
Bigger brain, more books, simple enough.
Right. But test time scaling is different. It's the idea that you can get a better answer not by making the model bigger, but by letting it think longer before it speaks.
So this is the whole chain of thought concept we've been hearing about.
Exactly. Instead of just memorizing that 2 + 2, 4, the model generates a sequence of reasoning steps. It might write out, first, I identify the two numbers. Second, I perform the addition operation. It verifies its own work. Sometimes it backtracks, it refines.
And the longer it spends doing this test time computation, the better the final answer tends to be.
That's the theory.
So logically, if I just tell a model to take your time, think step by step, it should just get smarter.
No, and that's the trap that so many people fall into. That's the core of the problem.
Okay.
If you just tell a standard off-the-shelf model to think longer, it usually just rambles. It produces more words, but not more intelligence.
It's verbosity, not cognition.
Exactly. You have to train it to use that thinking time effectively. You have to use reinforcement learning to reward it when it successfully navigates a complex problem and penalize it when it gets lost.
And this is where the nightmare begins for most researchers. This is where everyone gets stuck. Because they try to use the standard tools, specifically something called GRPO.
Right, Group Relative Policy Optimization.
And it fails.
It fails spectacularly in many cases. The authors of the DAPO research, they ran a baseline experiment just to prove this point. They took that same Quinn 2.532b model and tried to train it with naive GRPO, just the standard textbook implementation.
Right out of the box. And how did that go?
Not well. They only achieved a 30% accuracy on A.
30%, wow.
Yeah, and remember, DeepSeek's baseline was 47%. The final DPO score was 50%. So just using the standard algorithm leaves a massive 20-point performance gap on the table.
So the secret isn't just use GRPO, it's how you use it. The paper identifies 3 specific diseases, as they call them, that cause this failure. Let's list them out so we know what we're fighting against.
Okay, the first and perhaps most deadly disease is entropy collapse.
That sounds incredibly dramatic. Entropy collapse, is that as bad as it sounds?
For a model, yes, it's fatal. Entropy, in this context, it basically measures the diversity of the model's choices.
It's creativity.
Yeah, that's a good way to put it. It measures how unsure or creative the model is willing to be. You want high entropy during training because it means the model is exploring different ways to solve a problem.
You want it trying different keys in the lock, not just the one it found first.
Exactly. Entropy collapse is when the model suddenly decides, I found one key that sort of works, maybe it gets me 10% of the way there, and I'm never going to try another key ever again.
So it locks in on a bad strategy.
It stops exploring. It becomes deterministic. And if it locks onto a suboptimal strategy early on, which it often does, it never learns the complex reasoning you want. It turns into a zombie. All creativity is gone.
Okay, so disease 1 is the zombie model. That's a big one. What's disease 2?
Reward noise. This is a subtle but killer problem. In math or coding, you might get the right answer for the wrong reason.
Right.
Or the feedback signal just gets messy because the reasoning chain is so long. The model hallucinates a bunch of nonsense, goes on some wild tangent, but accidentally lands on the correct integer at the very end.
And the system, not knowing any better, says, good job, keep doing that nonsense.
Exactly. It reinforces the bad behavior. That creates a confusing, noisy signal.
And the third disease?
Training instability. This is what you see on the charts. The loss curves, the graphs that show how much the model is learning, just go haywire. They spike up, they crash down. It makes it impossible to know if your training run is actually making progress or just oscillating wildly.
So we have a zombie model from entropy collapse, a confused model from reward noise, and a volatile model from instability. This is the baseline failure state that everyone's been dealing with.
That's the mountain everyone's been trying to climb.
Enter DPO.
Enter DPO.
As you said, DPO isn't just one magic switch. It's an architecture, a system involving 4 specific techniques. I want to go through these one by one because this is where the actual innovation lies. The first one directly addresses that entropy collapse issue. They call it clip higher.
Right, clip higher. To understand this, we have to talk for a second about how algorithms like PPO or GRPO work. They use a technique called clipping.
Okay, lay this out for us. What is clipping in plain English?
Imagine you are coaching a basketball player. You want them to improve their shot, but you don't want them to change their form so drastically overnight that they completely forget how to play.
You want evolution, not revolution.
Exactly. So in the math of RL, there's something called a trust region. We basically limit how much the model is allowed to update its policy in a single step.
So if the model realizes, hey, this specific move is brilliant, and it wants to increase the probability of using that move by, say, 1,000%, the algorithm steps in.
The algorithm says, whoa, slow down. Let's just increase it by 20% for now and see how that goes. The standard value, which is denoted as epsilon, is usually 0.2 or 20%. This prevents the model from going crazy and destabilizing the whole training process.
Sounds reasonable. It's a safety rail. So why is that a problem?
The problem is the ceiling it creates for the underdogs.
The underdog tokens.
Exactly. Imagine a token, a word or a step in a math problem that currently has a very, very low probability, say 0.01%. It's a black swan idea, a creative leap. But the model thinks it's super unlikely to be correct.
Okay.
Now, what if that creative leap turns out to be brilliant? What if it's the key that unlocks the whole problem and leads to the right answer? The RL algorithm wants to massively boost its probability.
But the clipping stops it.
Right. If we clip the boost at 20%, that 0.01% only becomes 0.012%.
It's barely moving the needle. It's still basically zero.
Exactly. It's still invisible. It's still noise. The model can't launch new ideas because the safety rails are too tight on the upper end. It can't fund the long shot bets.
I see. But the tokens that are already high probability, the stuff the model already knows how to do, they don't need a huge boost anyway.
Right. If a token is already at 90% probability, a 20% boost is capped anyway. It can't go much higher. So the standard clipping disproportionately punishes exploration. It keeps the model stuck in exploitation mode, just doing what it already knows.
Okay, so what is the DAPO fix for this?
Decoupled clipping. This is the core idea. They realize that we need to protect the model from crashing, so they keep the lower bound tight. If a token is bad, we suppress it carefully, say by that same 20%.
So the safety rail for bad ideas is still there?
It is. But they raise the upper bound. They change the epsilon high from the standard 0.2 to 0.28.
That sounds like such a tiny change, just 0.2 to 0.28. That's really all it takes to fix it.
It sounds small, but in the world of probability gradients, it's a massive difference. Think of it like a corporate budget. Standard clipping is like saying no department can increase their spending by more than 20% next year.
Okay.
If your little R&D department has a budget of $1, you only get $1.20. You can never launch a new product line. You're starved for capital.
And meanwhile, the big established departments just keep getting their 20% on a huge baseline.
Exactly. Clip hire is like the CFO saying, okay, we still punish failure, but if your little R&D team has a winning idea, a breakthrough product, we will give you the funding you need to scale it fast. It allows the underdog ideas to get massive funding if they show promise.
And the result of this in training?
The entropy stays healthy. In their experiments, while the naive GRPO model saw its entropy just crash to near zero, meaning it stopped trying new things, the DPO model maintained a high, healthy entropy throughout training.
The model kept its mind open.
It kept trying new creative paths because it knew it would be rewarded for them if they worked.
Okay, so that's pillar one. Fix the entropy by raising the ceiling on exploration. That makes a ton of sense. Now let's move to pillar two. Dynamic sampling. This one addresses efficiency.
This one is fascinating because it deals with what they call the zero gradient trap.
The zero gradient trap. Okay, walk us through the logic here.
So in GRPO, you compare a group of outputs. You generate, say, 16 different answers to the same question.
Right.
Then you calculate the advantage of each answer relative to the group average. It's basically graded on a curve.
Okay.
Now, imagine the model is really struggling with a new concept. It gets all 16 answers wrong.
So they all get a reward of 0.
Right. And the average reward of the group is 0. So the advantage of any single answer, its score minus the average, is 0 minus 0.
So the math just zeroes out.
The gradient is 0. The model learns nothing. No update. Now, flip it. Imagine the model is really, really smart and it gets all 16 answers right.
They all get a reward of 1. The average is 1. The advantage is 1 minus 1, 0 again.
0 again. You are burning expensive GPU compute, paying for electricity, cooling, H100 rental time to generate 16 solutions, and the mathematical result is no update.
That sounds incredibly wasteful. As the model gets better, the problem gets worse. You're just spinning your wheels.
It is. It's a huge problem. As the model gets smarter, it starts getting more and more all correct batches. The training slows to a crawl. You are just burning compute for no learning signal.
So how does dynamic sampling fix this?
DPO implements a very clever filter. It actively discards the prompts where the batch is either all correct or all wrong. It just says, there's no signal here, throw it away. Next.
But wait, if you throw away data, your batch size shrinks. And in machine learning, a shrinking batch size usually means noisy gradients and instability, right? You generally want big, stable batches.
Spot on. You've hit on the key insight. That's the twist. You can't just filter. You have to oversample.
Ah.
They call it dynamic sampling because the system will keep pulling new problems from the data set and generating new batches until it fills up its quota with only informative samples where there's a mix of right and wrong answers.
So it forces the model to stay in the learning zone. It only trains on problems that it is currently struggling with, where there's a disagreement in the outputs.
It's the zone of proximal development, to borrow a term from education theory. It's like a good teacher who skips the questions you already know perfectly and skips the questions you have zero chance of answering and focuses entirely on the questions where you are getting, like a C-. That is where the maximum learning happens.
And the effect on training.
Much faster convergence.
Yeah.
Every single step is a high signal step. You aren't wasting cycles on the easy stuff or the impossible stuff.
That makes total sense. Brilliant. Okay, pillar 3. This one gets a little bit more into the weeds of how we calculate loss. This is token level policy gradient loss.
This is a direct response to what you could call the long chain of thought problem.
Okay, break that down. What is the standard way of doing this and why is it broken?
The standard GRPO calculates loss at the sample level. So imagine the model writes a 500-word explanation for a math problem.
Right.
The algorithm looks at that whole 500-word block and just says, this block is good or this block is bad. It averages the feedback across the entire sample.
Okay, so it's a pass or a fail for the whole essay.
The issue is that long chains of thought have hundreds, maybe thousands of tokens. If you just average everything out, the specific crucial reasoning steps buried in the middle get diluted.
Their individual contribution gets lost.
It gets washed out by the hundreds of other filler words. It's like giving a single group grade to a team project, where one person did all the brilliant work and 4 others just added fluff.
Yeah, that person doesn't get the credit they deserve.
Exactly. And there is a darker side to sample level loss. Long samples often contain what I call gibberish loops. The model might get stuck repeating a phrase.
I've seen that. It's spooky. It'll just say, therefore, 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 therefore.
Exactly. If you use sample level averaging, the penalty for those specific bad tokens that start the loop isn't sharp enough. The model might still get a decent reward if the final answer is right, even if it rambled for 20 pages to get there.
So token level loss changes this. How?
Yes. DAPO calculates the gradient for each individual token. This means that longer, more complex reasoning chains effectively get more vote in the gradient update. Every single step matters.
Ah, so the therefore loop gets a sharp penalty right at the source.
A very sharp penalty. And it specifically stabilizes the length of the response, preventing the model from just rambling to game the system. It sharpens the feedback signal dramatically.
All right, we are 3 for 4. We have raised the ceiling for exploration, we've optimized the batch for high signal, and we've sharpened the loss function. The final pillar is overlong reward shaping. This sounds like parenting advice.
It sort of is. It's about how you discipline the model when it talks too much.
Okay, so we've all been there. You have a context limit in the model, say 20,000 tokens. The model is reasoning beautifully. It's on the verge of solving the problem. It's deriving the fundamental laws of the universe. And then, bam, token 20,001. Cut off mid-sentence.
The hard wall. In standard training, if the model hits the context limit and doesn't output a final answer, the reward is MEDIC 1. Failure.
That seems really unfair. The reasoning was good.
It's worse than unfair. It's actively confusing for the model. The model doesn't know why it failed. It thinks, maybe my logic about the universe was wrong. Or maybe I shouldn't have used that formula.
It doesn't understand that the logic was fine. It just ran out of time. So you end up penalizing good reasoning just because it was a bit verbose.
Exactly. That's more reward noise.
So how does DAPO fix this?
It's a two-pronged approach. First, overlong filtering. This is simple. If a sample gets truncated, they just mask the loss. They just pretend it never happened.
We will not speak of this. Don't learn from it.
Exactly. It's better to learn nothing than to learn the wrong lesson. But the second prong is the really elegant part. Soft, overlong punishment.
The danger zone.
Right. They define a zone. For example, the last 4,000 tokens before the hard limit. If the model's response enters this zone, the system starts applying a gradually increasing penalty.
So it's a gentle nudge, a little tap on the shoulder saying, hey, you might want to start wrapping it up.
You're getting close to the edge, start converging on an answer. This teaches the model to be concise before it hits the hard wall, and it does it without wrecking its reasoning logic.
It teaches time management. That is incredibly human. It's like a professor saying you have 5 minutes left on the exam.
And it works. The outcome is that the model learns to solve the problem efficiently within the given constraints.
So those are the 4 pillars: clip higher, dynamic sampling, token level loss, and overlong reward shaping. It sounds like a really robust, well thought out engineering stack.
It is.
But the proof is in the pudding. Let's talk about the results.
The scoreboard is impressive. As we said, they use the AMI 2024 benchmark.
And again, for listeners who don't know, AMI is tough. It's not just solve for X. It requires multi-step creative problem solving. These are problems designed to stump very smart high school students.
Correct. So they use Quinn 2.532b as the base model. The baseline DeepSeek R10 implementation on that model scored 47% accuracy.
Okay.
DPO scored 50% accuracy.
Now, some people might hear 3% and shrug. But gaining 3 percentage points on a benchmark like AIM is non-trivial. That's a huge leap at that level.
It's very, very difficult. But again, the real headline for me isn't just the 3%, it's the cost, it's the efficiency.
Yeah.
DAPO reached this score in half the training steps of the DeepSeek run.
Half the steps. Let's just sit with that for a second. That has huge implications for democratization. It means you don't necessarily need a massive multi-million-dollar cluster to train these things anymore.
Exactly. A smaller lab, a university, or even a determined individual has a much better shot now. Now, there is one more detail in the experimental setup that I found really clever. It's a bit of a hack, but it speaks to the messy reality of ML engineering.
This is the dataset transformation, right?
Yes, the integer transformation.
I want to talk about this because at first glance it feels like cheating, but it's actually just really smart engineering.
It is. So math answers are messy. You have square roots, fractions, pi, complex expressions.
Right. If the correct answer to a problem is 11 minus 2 times the square root of 6, checking that programmatically is a total nightmare.
It is. Is 11 2 squared 6 the same as the full decimal expansion? What if the model writes it as 9 2 squared 6 plus 11? What if it uses LaTeX formatting?
Right.
If your answer parser fails for any of those reasons, you give the model a 0 reward, even if it was right. That is a perfect example of reward noise.
You're punishing the model for a formatting issue, not a math issue. So what did the DAPO team do?
They manually went through their training set, the 17,000 problem set called DAPO math, and they transformed the questions. They changed the question so that the answer would always be a simple integer.
Wait, how do you do that? You can't just change the answer to a math problem.
You change what you're asking for. Instead of asking find x, where x is that complex root, they rephrase the question to be, the answer is in the form a plus b times the square root of c. Please find the value of a plus b plus c.
Oh, that is brilliant.
So the answer is just 19.
Because checking if the model's output is 19 is binary. It is either 19 or it isn't. There are no parsing errors.
Exactly. It creates a perfectly clean, unambiguous reward signal. The model still has to do all the hard math to find A, B, and C. It can't cheat the reasoning, but the verification step becomes error-free.
It removes the parser lottery from the equation.
It does. And this massive reduction in reward noise is likely a huge contributor to their stability and fast convergence.
I want to move on to what I think is the most exciting part of this, the emergent behaviors. Because we can talk about models optimizing reward, but at some point, that optimization starts to look an awful lot like thinking.
This is the ghost in the machine part of this show. Does the model actually understand what it's doing, or is it just a very sophisticated mimic? The DAPO paper provides a case study that really argues for the former, or at least a very, very convincing simulacrum of it.
This is the tetrahedron problem.
Right. A complex 3D geometry problem involving volumes and angles. A real tough one.
Walk us through the evolution of the model on this problem. What happened early in the training versus late in the training?
Okay, so in the early checkpoints, the model behaves like a standard LLM. It reads the question, it grabs some formulas that look related, and it rushes to an answer. The volume is X. It's basically guessing or using some shallow heuristic pattern matching. It doesn't check its work.
It's confident and almost certainly wrong.
Exactly. But later in the training, after all these DAPO-driven RL updates, something shifts. The model starts solving it using coordinate geometry, which is a valid but very brute force calculation method. It's getting messy, lots of algebra, very tedious.
Okay, so it's working, but it's taking the long road. And
Then, spontaneously, in the middle of the generation, it outputs this exact text. It writes, however, wait a moment, let's rethink about the dihedral angle involving planes in a more thoughtful geometric way.
wait a moment, it paused itself.
It stops itself mid-calculation. It abandons the messy coordinate geometry calculation and it switches to a much cleaner, more elegant, pure geometric conceptual approach.
That gave me chills when I read it in the paper. Was it programmed to do that? Did the prompt say anything like, if you get stuck, try a more geometric approach?
No, not at all. That's the magic. That behavior self-correction, backtracking, switching strategies from a brute force one to an elegant one that was not explicitly programmed. It emerged solely from the relentless pressure of the RL.
So it learned that strategy was a dead end.
The model learned, through trial and error over millions of examples, that if it rushes, it gets a 0. If it gets stuck in messy algebra, it's more likely to make a mistake and get a 0. The only reliable path to the reward was to stop, reflect, and find a better, more robust method.
That feels like the definition of reasoning. It's not just processing, it's metacognition. It's thinking about how you're thinking.
It's the closest we have to it in a machine, and the metrics back this up. If you look at the entropy charts for DAPO, unlike the naive methods where entropy crashes to 0, the zombie model DAPO maintains a slow, healthy upward trend in entropy throughout training.
So it's always keeping its options open.
It suggests the model is constantly keeping its mind open, constantly evaluating if there's a better way to do things.
So what does this all mean for the field at large? We have a system that works, it's open source, and it fits on a reasonable GPU setup.
The biggest implication, I think, is democratization. Until now, reproducing something like OpenAI's O1 was seen as a big lab problem. You needed thousands of H100s and a giant team.
A huge budget.
DAPO proves that you don't just need a massive proprietary cluster to train reasoning models. You need a disciplined, intelligent algorithm.
And you need the right framework to build on.
Right. They built this on the Volsingen RL library. This is also open source. This is a big deal.
Right.
It moves RLHF from being this collection of black magic scripts that only one engineer in the company understands,
right,
to a reproducible, stable engineering stack that anyone can use.
Now, surely there are blind spots here. Limitations?
Always. This paper focuses very heavily on math. The AM benchmark, the integer transformation hack. Does this transfer to coding? Probably coding has a similar structure of right-wrong answers.
But does it transfer to creative writing or legal analysis?
That's much less clear. The reward signal is fuzzier. Wait a moment, let me rethink the emotional arc of this poem. Is a very different reward signal than the answer is 19.
A much harder one to model.
Exactly. And that integer transformation, while it was brilliant for their experiment, is also a limitation. In the real world, we need models that can output complex mathematical notation. If we only train them to output integers, are we crippling their ability to express complexity? That's a big open question.
So it's a fantastic proof of concept and a blueprint for the algorithm, but maybe not the final production pipeline for a generalist agent.
I think that's the perfect way to put it. As a blueprint for how to stabilize the learning of reasoning, it is a landmark contribution.
All right, we've unpacked the tech, we've seen the results, we've talked about the implications. Now it's time to get a little crazy.
My favorite part of the show.
It's time for Novel Notions. This is the segment where we take the core concepts from the paperclip hire, dynamic sampling, the whole DAPO philosophy, and we extrapolate. We pitch outlandish but plausible ideas based on where this tech could go.
With the very important disclaimer.
Yes, disclaimer. This is for entertainment and speculation purposes only. Do not build your next startup on this without, doing your own research.
And maybe giving us some equity.
I'll go first. I'm thinking about dynamic sampling. The idea that DAPO filters out the questions the model gets 100% right or 100% wrong to focus on the edge cases.
Right, the zone of proximal development.
Exactly. I want to take that to its logical, terrifying extreme. I call this concept the panic room architecture.
The panic room. Okay, I'm listening. Sell me on this.
Imagine a training environment where the model never sees a problem that it is comfortable with. Ever. We build a generative adversary, another powerful AI whose sole job is to generate synthetic problems that the target model has exactly a 50% chance of solving. No more, no less.
So you are mechanically keeping the model in a state of maximum cognitive stress at all times.
Perpetual crisis. As soon as the model starts to get good at algebra, the panic room stops serving it algebra and starts generating problems in topology. As soon as it masters topology, it switches to non-Euclidean geometry. The model never gets that dopamine hit of an easy win. It is perpetually fighting for its life in the gradient descent valley.
It's like training a Navy SEAL by making sure they never, ever have a comfortable day.
That's the idea. The thesis is this could compress years of learning into weeks. You would create a savant node. It might be socially awkward. It might not be able to tell you the weather or write a poem. But if you give it an impossible problem, it has been forged in the fire of impossibility. It's a specialized reasoning core trained exclusively on the bleeding edge of failure.
That is both terrifying and brilliant. You're maximizing the gradient signal at every single microsecond of training. The main challenge, I guess, would be that the adversary, the problem generator, would have to be significantly smarter than the student model.
It would have to be a next-generation model itself.
But if you could build it,
Yeah.
the efficiency per token of the learner would be completely off the charts. I like it, the panic room.
That's notion one. What have you got?
I'm fixated on clip higher, the idea that we can decouple the safety rails from the exploration potential, that we can allow those underdog ideas, those low probability tokens, to rise to the surface very rapidly.
Okay.
So I call this the doubt engine, or for a more dramatic title, the Oracle of Chaos.
Ooh, I like Oracle of Chaos. That's good.
So we usually train models to be helpful, harmless, and honest. We want the most likely answer, the consensus answer, the one that reflects the middle of the probability distribution.
Right, the safe answer.
But what if we applied clip higher to something like strategic forecasting, but we cranked the upper clip parameter, the epsilon high to extreme levels, say 0.8 or even 0.9, and then we inverted the reward function.
Inverted how? What are you rewarding?
We reward the model for finding reasoning paths that are logically sound, each step have to be valid, but that lead to a statistically improbable conclusion.
You want to train an AI to be a conspiracy theorist.
No, not quite.
Yeah.
I want to train it to be a black swan detector. A standard model ignores low probability collapse scenarios because of normalcy bias. It's trained on data where things mostly work out. So it says the market will likely go up, the supply chain will likely hold.
Because that's what the training data says usually happens. It's biased towards the mean.
Right. But if we use this extreme version of clip higher to massively boost the exploration tokens that correspond to fringe but logical causal chains, we could build a model that specializes in detailing exactly how things could fall apart.
So you ask it, what happens to the global economy in 2026? The standard model gives you moderate growth of 2-3%. The Oracle of Chaos says, okay, here is a highly specific 5-step sequence of minor events in shipping, agriculture, and finance that triggers a global liquidity crisis.
Exactly. It ignores the median outcome and obsessively maps the tail risks. For an intelligence agency, a hedge fund, or a safety engineering team, this would be an invaluable tool. It's a machine designed specifically to overcome the optimism bias inherent in standard RLHF.
That is fascinating. Weaponizing the exploration parameter to hunt for disaster scenarios.
It's the ultimate digital stress tester for any complex system.
Well, there you have it, the panic room and the Oracle of Chaos. 2 things you can build with the ideas from DPO if you have enough GPUs and very little regard for your own sanity.
Indeed.
And that brings us to the end of this deep dive. To recap, DPO fixes the plumbing of reinforcement learning so the water of reasoning can actually flow.
And it shows that it's not magic. It's not sentient. It is decoupled clipping, dynamic sampling, token level loss, and some very clever reward shaping.
It demystifies the hype. The magic of O1 and R1 is actually just really, really good engineering.
Disciplined, open, reproducible engineering.
We will have the link to the paper and the code in the show notes. Go check it out. Clone the repo. Try to train your own savant node.
Just keep your learning rates low and your gradients steep.
And keep your entropy high. Welcome to the era of open reasoning. Thanks for listening to TalkTensors. We'll see you next time.
Goodbye.